I wanted to talk about we ran an Optica incubator at back in December together with Inder Manga and Wenji Wu from ESNet and Anuj Agrawal from IIT Delhi. And some interesting findings came out of that. And I thought it's particularly relevant to this community here. And so I wanted to take some time and talk about that and give some of my own personal perspectives on topics that came out of this meeting. Let's see. So there's this doesn't seem to be. Try that. Okay. Okay. Yeah. So I don't know if folks are familiar with the Optica incubators. It's a nice format where it's invitation only. Although we tried to broadcast widely, and anyone who wanted to come was welcome to come. But they hold it at the Optica headquarters in Washington, D.C. You spend 2 days. And in this case, we wanted to really bring together researchers, academics, industry folks to talk about quantum networking. And with the perspective that, of course, quantum networking is rapidly maturing, and there's many challenges that are coming out of that. And in particular, we're interested in the notion that we're moving from science labs to engineering test beds, right? And so, and this sort of transition involves many disciplines and has many challenges associated with it. So we wanted to figure out the current status of this transition, right? And what the emergent research challenges are that we might bring attention to help accelerate the development of solutions in this space. And in particular, I want to focus on systems research. And when I talk about systems research, here's our Google definition. So I like it very much. So a set of things working together as parts of a mechanism or an interconnecting network, right? And really emphasizing, so you're bringing devices together to build something, right? And in particular, I want to differentiate from other types of systems research and emphasize what I'm going to refer to, and you have to forgive me for this, engineering systems research, right? Rather than mathematical or physics-focused systems research. And so based on practical hardware that can be built in a lab. And actually, so Anton's talk that he just gave, I thought was brilliant, and it's a beautiful example of kind of a mathematical or physics-based approach and an analysis of this problem. But it didn't really require you to understand how you're going to make a GHZ state, right? And today, I don't know that we know how to make a GHZ state from actual physical devices, right? And it has been made practically. So here with engineering systems, we're going to talk about, okay, let me take some devices that I can actually build something with and then start to actually say implement what Anton was talking about and measure the performance of that, right? And so that's what I would refer to as engineering systems research. And I don't want to diminish, again, the math and physics is incredibly important, and it tells us about the physical bounds and answers a lot of important questions that we need. But eventually you need to get some hardware devices and start to put them together and do research on that. And that's what we really wanted to focus on in this incubator that we ran, and what I want to talk about here today. And this is I'm someone who I started out as a device person in physics, and then eventually started working on systems, and now I consider myself fully a systems person. And you often hear, and certainly in the optical systems community that I'm from, people are always asking, are you a device person? Are you a systems person? This kind of thing. And it's that divide that we're talking about here, right? And so taking my perspective of optical communication systems, so we can look back at what happened in terms of developing devices in optical space. So in the 1970s, we finally got our double heterojunction semiconductor lasers. That's a source that we can use to send signals in a communication system. And we got the fiber loss in the 1970s going to 1980 down to a level where we could really build networks out of it. The other thing that happened around this time that didn't receive a lot of attention is we actually came up with connectors to connect fibers together with relatively low loss. So we started to get basically these components that allow us to build systems. And about this time in the 1980s, we see the first, what I would call engineering systems research coming out in the optical communication space. And here's some nice examples, some Dave Payne's work here. and some work out of Japan, Suzuki's lab. So people started putting these components together and building these systems. So I would argue that in the quantum world, we're kind of at that point right now, right? So actually, we've had sources, and in this case, the source isn't just a laser that you turn on and off. It's actually a photon generator, so a pair source, something like a spontaneous parametric down conversion source. And so you create these entangled pairs. We have single photon detectors for detecting those. And we have switches and multiplexers, which we had from the classical communication world. And sure enough, people have started to put together physical systems. So this is a very nice work out of the Austrian group, and also some work at Bristol, looking at basically taking a pair source, combining it with switches and multiplexers, and distributing entanglement to many nodes in a network. So we can actually build networks, distribute entanglement, and do experiments with those, right? And that's where we are today. So now, if we look at what happened with optical systems, maybe it'll give us some perspective on where we're heading in the quantum space, right? So this is a nice chart that looks at the history of optical communications from the 1980s, what I was just talking about there, where we have the first systems emerging. And first off, we see two trends here. One is there's the commercial trend and then the research trend. And you'll see that basically research results are ahead of the commercial results by about 5 years generally, okay? So, and that was typical throughout most of the history of optical communications. And we also, you can see there's a trend here for systems, and here we're talking about multi-wavelength systems versus transceivers or components, kind of the main devices that you're hooking up over these systems to communicate with. So your transceiver development, and both of these, both the individual transceivers as well as the systems of transceivers, developed rapidly over basically many orders of magnitude of capacity. So we're looking at system capacity per fiber as a function of the year. And so then if we go forward here, if I focus you down to the beginning of this trend here. So first off, basically you could argue that entanglement systems are here, right? We're just at the very beginning of this. And in fact, amplified systems for optical communications didn't start until about 10 years or so after the first systems started to get built, right? And so as in the quantum space, we don't have repeaters yet. So you could argue that this is where eventually we will have repeaters. And so in the pre-repeater world, we're in this situation where all we can do is have kind of a one-hop communication system that we can build up. And so entanglement systems, we need reference architectures and we need engineering practices in order to create the similar type of many decades and many orders of magnitude capacity enhancement of our quantum networks over time. So this is what I would argue that we're trying to head towards, and we're trying to look at what are the systems practices and research that we need in order to start moving up this kind of a trend, right? And first off, I want to say a little bit about my own background and some of the work that we're doing at Trinity College Dublin. And actually, this is some work also that we're doing with Bulat Bosch and Marco Ruffini. We've been looking at using wavelength selective spontaneous parametric down conversion sources. So the most common approach is to use an unheralded approach where you have an SPDC, and the output of that you send to some sort of demultiplexer or wavelength selective switch. And then you have different output ports with your signal and idler photons that have been basically wavelength sliced if you have a broadband source. And there's this unheralded approach, but then there's also this heralded. Whoops, we got a different type of pointer now. Let's see, I think there I switch it back. With the heralded approach, actually, and they sometimes refer to a zero added loss multiplexing. This was developed by a group at Arizona and MIT. You take two SPDCs and you take the idlers, and then you can mix them together to basically herald when you have your signals going out. And if you put some demultiplexers on there, then you get wavelength selective heralding, which then you know the wavelength of your entangled photons, which would be polarization entangled there, right? So we've been looking at those types of sources. So and in a practical sense that you can build again, and going one step further and starting to say, okay, how do we build networks out of them? And so you could place sources at different locations around a network. And so now you're going to send your signals and at different wavelengths to your end nodes and create entanglement between, say, two nodes in a network. So we have a number of publications, ICC and JSAC, that have come out of this. And one of the things that we found was that it leads to some very interesting wavelength routing rules. And again, looking at this as an optical networking problem. So there's a lot of research that goes on in what we call routing and wavelength assignment for classical networks. So we need to do the same for these quantum networks. And in fact, in quantum networks, you have the strange situation where your signal and idler might be at different wavelengths. So now you're routing signals at very different wavelengths to two end nodes that are going to be entangled, but those photons might be coming from a third node, which is actually where your source is, right? And which is a really odd wavelength routing problem, and leads to some interesting results. And so we've published some work on that. So this is taking, again, so everything that I'm showing here is built on components that you can build in a lab. And in fact, we're doing exactly that. We're building this up in a lab and starting to do some experiments on these types of systems. But initially we did some paper studies and some nice analysis there. I want to just tease a little bit. So one of the things that we're looking at kind of beyond that is, well, we need to, in the classical optical communications world, we need to simulate and emulate our classical systems so that we can understand them and engineer them better. And so we're looking at, for the quantum network, how do we simulate a quantum network, and ask the question, should we use a quantum computer to emulate or simulate quantum networks, right? So the quantum networks involve these quantum transmission effects in the links, and we do quantum processing in the nodes. There's a number of nice classical simulators for quantum networks, such as Sequence and NetSquid, right? And actually, I mean, it's very common to set up, say, a quantum teleportation example type of calculation that you can do in NetSquid or on any of the quantum computers that are out there today. But here we wanted to say, okay, so how do we simulate the actual transmission across a fiber, the photon loss effects, together with those end processing, and actually simulate a quantum network that way? And so I'm not going to say more about that. So Bulat is here, and on Friday, he has a talk, Emulation of Entanglement Distribution Networks Using Quantum Computers. This is at 4 p.m. on Friday, so you're going to have to stay the whole week, okay? But it's worth it to hear Bulat talk about this really interesting topic. Okay, so now I want to get back to this incubator that we ran back in December. And the key challenges areas that we looked at were, well, quantum network applications. So can we start to talk about reference architectures and these kind of evolutionary pathways, considering the different types of applications? And in particular, quantum data center networks are an important area to look at. And then also there's the case of if you want to involve quantum repeaters and longer distance entanglement-based QKD networks. I should say that, you know, it was in the US. There's a lot of US folks there, so there wasn't a lot of talk about QKD. And so we probably need to do more on the QKD side. I'll mention just briefly. So we need to know what are the hardware bits that we're going to put together to make these systems. So we spent some time talking about quantum networking hardware, what's out there today, what's the state of the art, and where things are going. And then talking about architectures and protocol stacks. So as we start to put these components together, what architectures are people looking at, what's available, and what protocols do we need for that? And then lastly, but I think most importantly, is we delved into this question of network systems engineering and practice. So we need to develop test beds and laboratory practices to characterize these systems. We need metrics to understand and compare performance across the systems, and looking at these experiments that are focused on system level performance, scalability, reliability, and cost. So those are the things that we looked at. Again, we wanted to develop shared understanding, identify R&D pathways, and start to generate some collaborative materials. And I should say that we're in the process of writing up a lot of the outcomes from the workshop right now, but so I won't go into all of that, and there'll be more to come, but I wanted to give you a sneak preview here. So this was so we had 53 attendees, we had 18 lightning talks, 3 roundtables, some breakout sessions, and let me get into some interesting things that came out of that. So first off, development of a pathway for quantum networks. So there were 2 main paths that were identified. So you have the QKD path, right? So where we need to add capacity, switching, and distance, but also functionality, go into device independent or measurement device independent, twin field, and starting to move towards entanglement in that case. We didn't spend a lot of time on that. So most of what we focused on was the quantum computing side of things. And the interesting thing was that it really emerged that there's strong consensus that in the quantum computing space, we're going to develop data center networks, right? To scale quantum computers. And initially, networks that are point-to-point interconnects, maybe with some switching for some reconfigurability. Now, the key is, of course, you need transduction in these computing systems, but that will come. And then we will basically, networks will evolve from the data center network. And it seemed like there was, again, wide consensus that we're going to have data center quantum networks first, and then from there, at least from the entanglement point of view, and from there, networks will grow. And loss-limited metro campus networks will quickly follow. And then, of course, repeaters would evolve over the long term. And speaking of repeaters, so we're heading towards fault-tolerant quantum computing. I think IBM has a roadmap where within the next 5 years, they're going to have fault-tolerant quantum computing. IonQ has a similar roadmap. Let's hope that they hit their roadmaps for the sake of all of us and the whole discipline. But all of these folks basically will need to interface to optical networks in order to scale. So no one is talking about doing fault-tolerant quantum computing, that at least that I'm aware of. There could be some that are talking about achieving that. And here we're talking about millions of qubits without being able to communicate over an optical network. All right, so they need to solve the transduction or wavelength conversion problem. So if they do that in the next 5 years, then we will have transduction and wavelength conversion, and we'll have fault-tolerant quantum computers. So, and basically, a fault-tolerant quantum computer is a quantum repeater, is it not? Right. So what can you do with that? You could basically create a repeater out of that. Now, there was a lot of discussion about this, that once we have fault tolerance, okay, then we can repeat and we can error correct and we can enable our connections to keep moving on. And so, but there was some thought that we will build quantum repeaters that are essentially purpose-built quantum computers, and those repeaters would be likely more parallelized, let's say, and designed to kind of like today's packet routers, right? They're computers, but they're really made for just routing packets. So we'll have quantum computers just made for routing qubits across a network. And again, they will build on these, the transduction and conversion that'll come out of the quantum data centers and so forth. And there was some discussion. So there's interesting ideas around ancillary memory or processing technologies such as color centers for speed and parallelism that might be exploited as well. Okay, so I want to talk a little bit about layering. So there's a lot of discussion at this event on this, and there's 2 prevailing approaches. One is that layers can be defined based on the separation of function and objectives, and maybe there'll be 3 to 5 layers that would basically be put in place to simplify your engineering of your overall system. And the other approach is that we'll have a quantum will have a data plane and a control plane, but that's difficult or impossible to define layers equivalent to today's classical network layers. And one of the motivations around this is that, well, you can't achieve a clean separation of concerns if you're talking about entanglement. when your photons moving across the network, they're entangled with your computers, and anything that you do across all the layers are going to um, be interfacing with the flying qubits that you have in your network. So your network is intrinsically coupled to your computing. And so how do you get a separation of concerns? So and the other big point here is that entangled photons aren't information being transmitted. They are a resource that is part of quantum computers. And they don't need to be compatible with the classical stack. Now we have concepts today like software-defined networking that's actually used to allow us to do control across layers and break the layering that we have in classical networks. And that allows us to regain certain efficiencies that we lose from using layers. And so you could argue, why does quantum need to use layers? We could go straight to kind of an SDN type approach. And if the metadata is decoupled from the payload, then the latency is often too high and the system won't scale because of the low coherence budget. So, so another question that came up there is, where does one draw the line then between quantum computing and quantum communication, right? Is the communication part of the computer? This was an interesting discussion that came out. So if you think about these two paradigms now, so you can entanglement as a resource. So the idea is that you're not really communicating with it. You're basically allocating it the same as memory or processing, right? So I'll basically create a distributed quantum computer shown in green across my network, which involves my square boxes here are your quantum data centers or my QPUs, if you will. And then I connect up a set of those across a network, and I create this distributed quantum computer. And it's all a fully integrated device. And the entanglement that's connecting these QPUs is a resource the same as your memories and your compute, right? And you'd have another one, distributed quantum computer too. And then the other view is that I have these various quantum computers, and I'm going to send these EPR pairs or I'm going to send flying qubits, entangled photons across the network and create entanglement. So in this view, I'm viewing entanglement really as communication. It's something that I'm routing around a network, and I'm creating this. It's kind of like I'm sending information instead. I'm sending qubits that are entangled with my computer, and I'm going to then use them for say teleporting information and so forth, right? And so there was a lot of discussion on this, and I think it's a really important question. So as a resource, we're allocating, generating, and maintaining entanglement across a network, and that's a physical layer operation. And there's a separation of concerns in that everything is a data plane in that case, and then above that you would have a control plane that's going to manage your distributed computing and so forth, right? Now entanglement as communication. Right, the physical layer involves transmission and switching of entangled photons, kind of like your optical physical layer. And then you have the potential to define additional layers for switching and routing of entanglement, kind of like your Ethernet and IP layers. And then also you might have capacity management in that case. So you might have a kind of TCP type layer there. And I think, so this gets down to, if you view entanglement as a resource, you really only have data plane and a control plane. Whereas if you want to look at entanglement as communication, then you might start to identify these different types of layers that have analogs with your classical layering system. Okay. And then, so I want to call out, so Sarah Cacciapuati at the University of Naples, she gave a really excellent talk, and she was really driving this whole notion that so we need a quantum computing control plane to build a scalable quantum network. And so you're going to act on, your control plane needs to act on quantum header or metadata information, and quantum dynamics are too fast and non-local for classical signaling, if you think about it, right? So you can do an action at one node, and that could affect nodes all across the network. So I really need a quantum computing based control plane in order to be able to manage and control that type of network. And so this concept and quantum control plane, it won't replace a classical control plane. You need both, right? But that we need that capability for scalable networks. And there's a potential then to define kind of a control architecture evolution where you might start with basic quantum links with classical control and evolve to networks with full quantum control. And the possible to chart out different hardware functional levels and ask what applications can emerge or be enabled by this. Okay, so just to wrap up, so we identified a number of important directions for systems research. So we mainly focus on entanglement distribution, the evolution out of data center networks and fault-tolerant quantum computers. I would argue from discussions that we had there that layers are still wide open. I know that there's a lot of activity in the standards area, but I think there's a lot to be done there. And there's these questions around to what extent should quantum computing-based control be used. And other topics in the incubator included application-specific functions, the role of testbed standards, system abstractions, tools of trade, accepted practice. I didn't get to get into those here, but we'll be coming out with a number of papers and other outputs from this. And so we're looking forward to sharing that. And we're also considering new workshops and symposiums on quantum network systems research. I think, again, this is a great community that we have here. I'd welcome all of you to participate. We like to maybe cooperate with things that's going on with this community here. I think we need more folks bringing together, sort of actually learning from classical systems research, but also then building up a new quantum systems, engineering systems research effort. Okay, thanks for your attention.
So, Daniel, thank you. Do you have a short question for Daniel from otherwise? Yeah.
Yeah, thanks for your talk. So for the quantum control plane, you said that the entanglement dynamics are way too fast for classical signaling. So what kind of signaling do you envision for this control plane then?
So, well, first off, I would recommend that you contact Sarah. So that was really her. She was the main person driving this approach. But well, you could imagine if I have to plan a network, right? So I don't know about the signaling, but I have to plan a network, and so I would want to run some computations that take into account all of these non-local effects and quantum. And so if I want if I have some sort of simulation or calculation that's based on quantum effects, to do that scalably, I need quantum computing, right? So I think for me, there is a clear example of where if I'm, for example, when I do wavelength routing around a network, I need a model for the network and I need to do some computations. And often we run into problems because most of our distributed network algorithms in the classical space are NP hard, right? And so we use all sorts of heuristics and trying to get around that and things. But more so in the quantum space, if you're now talking about routing entanglement, I need to do these types of computations and they're involving these quantum effects, it makes sense to be using some sort of quantum computational element to kind of optimize and come up with solutions for those controlled decisions. That would be my argument.
Thanks.
Paul, can I add a question? Nobody has ever been talking about data rates possible on entanglement as a communication network. What data rates are we talking about today?
So by data rates, I would take that as e-bits per second, entangled bits per second, let's say. And if you're talking about something with repeaters, then people are looking at sub 1 e-bit per second, okay? We're very, very, very slow. But in other cases, if you're doing direct entanglement distribution, then you can get millions of e-bits per second. So
Okay, so thanks a lot, Daniel.